Look closely at an empty void. In classical physics, nothing happens here. But mathematically, a pure vacuum field is dynamic, and the ripples that emerge from this empty space are responsible for the structure of our universe. This is the cosmic microwave background, a map of temperature fluctuations from the early universe. It is the strictest test in modern cosmology. Any model of the universe must perfectly predict the exact distribution of these hot and cold spots. The standard model relies on a specific assumption to make the math work: cold dark matter. Without a non-interacting cold particle to anchor the gravity, high-velocity particles would stream freely through the early universe, erasing the small-scale structures and damping the higher acoustic peaks we see in the data. But cold dark matter is inserted into standard equations phenomenologically. Physicists manually add an independent mathematical term to fit the observed data, rather than deriving its existence from fundamental initial conditions. Dynamic vacuum field theory, or DVFT, takes a different approach. This equation describes the pure vacuum action in DVFT. The dark matter term is noticeably absent. The theory proposes that we do not need to invent an independent dark matter particle. Instead, it provides a complete dynamical derivation, calculating how the observable universe forms purely from the initial conditions of the vacuum itself. Reproducing the CMB power spectrum requires tracking the chronological causal sequence of underlying vacuum dynamics. The sequence begins at the very earliest stages of the cosmos. This graph shows the vacuum potential. We start with a pure phase vacuum, resting precisely at zero density, an unstable maximum. The linearized equation around this point describes a classic tachyonic instability. The vacuum cannot remain here. A slight perturbation causes inevitable exponential growth. This triggers a rapid, nonlinear roll-down into a stable minimum, establishing a physical vacuum mass density of roughly 6 × 10 to the -27th kilograms per cubic meter. Dropping into this trough releases massive potential energy, marked as delta V, powering an inflation-like expansion. The background scale factor and the Hubble parameter, the metrics that describe the expansion of space, are directly set by the specific energy released during this vacuum stage. Physically, this roll-down triggers the breakdown of global phase coherence. The smoothly unified vacuum shatters, producing highly localized vibrating excitations. A single tachyonic instability establishes both the macroscopic geometry of the expanding universe and the microscopic localized excitations. These excitations set the stage for the first physical matter. The immense disequilibrium energy and the rolling phase from that initial instability generate a powerful, effective electric-like field strength within the vacuum. This field strength is so intense that it forces the vacuum to produce fermionic defects, the earliest form of matter particles, through a Schwinger-like pair production process. The initial distribution of these newly produced defects is defined by this raw momentum spectrum equation. When we plot this equation, we see the defect momentum mapped as a curve. Notice the wide distribution across the horizontal axis. The problem lies in this high momentum tail. The wide spread means these defects are moving very fast. In cosmological terms, this particle distribution is extremely hot. Fast-moving particles create a free streaming problem. If these hot defects persist, their high velocities will allow them to escape early gravitational wells, erasing small-scale structure. The Schwinger mechanism explains matter creation, but those particles move too fast to clump into dark matter. Without a way to slow them down, they would completely destroy the higher peaks we observe in the CMB. DVFT resolves this by demonstrating that the vacuum itself acts as a rigorous physical momentum filter, dynamically cooling these hot defects into stable relics. This is the full cosmological relic equation. It modifies the raw, hot production spectrum with mathematical filters. First, look at the vacuum decay term. Because the post-roll vacuum is stiff, high-momentum particles are rapidly reabsorbed. Next, annihilation and topological locking terms further damp the remaining distribution. Modes are locked in place, stripping away heat. This achieves a strict condition. The derivative of the survival probability must be negative, guaranteeing exponential suppression. The result is a mathematically verified cold relic. At the time of recombination, the root mean square momentum is a tiny fraction of the particle's mass. The momentum filter ensures the free streaming length of these defects is far smaller than the sound horizon. The vacuum naturally produces a clustering sector that precisely replicates the behavior of cold dark matter. We insert this filtered cold relic distribution into the collisionless Boltzmann equation, evaluating it in conformal Newtonian gauge to track its evolution over time. This phase space distribution generates the multiple hierarchy. Alongside photons and baryons, these cold defects directly source the Einstein equations governing the universe's expansion. This chart shows the stage C numerical implementation. The theoretical power spectrum derived purely from DVFT vacuum dynamics tightly weaves through the actual observed data points of the cosmic microwave background. The model accurately reproduces the primary acoustic peak. This proves that the vacuum defect sector supplies the necessary gravitational wells before recombination. Furthermore, the higher-order peaks align perfectly. The physical momentum filter successfully restricted the particle velocities, preventing the erasure of these smaller structures. Minor deviations in the high multiple numbers are the specific predicted results of the tiny residual velocity dispersion left over from the momentum filter. The numerical fit maps an uninterrupted chain. Starting from one unstable vacuum scalar field, equations compute the specific complex geometric pattern of the observable universe. We can now return to the complete vacuum action equation. It unifies the entire chronological sequence. The density term, ρ, drops into the tachyonic trough. This establishes the classical geometry, gravity, and inertia of the universe. The phase term, theta, dictates quantum coherence. When that coherence breaks down, it creates localized matter, which the vacuum filters into stable, cold relics. The CMB is a fossil imprint of this quantum-coherent vacuum dynamics evolving into classical gravitational structure. Proving this requires comparing the derived spectrum to the most precise observational data available, the Planck satellite mission. The upcoming Stage D analysis will apply a Markov chain Monte Carlo inference on the fully constrained set of DVFT parameters to run the definitive test against Planck data. By tracking the causal chain of the vacuum, DVFT derives the exact clustering abundance dynamically from first principles. The mathematics map the early universe without relying on the phenomenological insertion of dark matter.